Bienvenue à tous et à toutes. I'm going to switch to English. So welcome everybody. This is both the last session of my series of lectures on ultra-cold fermions in optical lattices. And it is also embedded in the 4 days, I guess, meeting devoted to our trick software users and developers. So welcome to both crowds, which have a non-zero intersection. So today is a bit of a special format for the lectures in view of this special circumstance. So we have a mini symposium which is devoted to various computational methods for strongly interacting fermions, admittedly quite strongly oriented towards diagrammatic Monte Carlo, but not only. The first speaker is Thomas Schäfer. So it's a great pleasure to welcome you, Thomas. Let me tell you a few words about Thomas. I guess many people in the room know him. So Thomas did his PhD at the TU in Vienna. And then he moved to Collège de France, where he was a postdoc with me and Michel Ferrero. And we had a wonderful time there. We went through the COVID experience, which allowed us to focus for several months on a single paper, which was actually a great experience. Since then, he moved to the Max Planck in Stuttgart, where he's a junior group leader. And he's going to tell us today about two of his favorite things to which he contributed in a major way. And, well, I'm not going to anticipate on the talk, so I will let you have the floor.
Merci beaucoup, Antoine, et bonjour, bienvenue. C'est un grand honneur, en fait, de donner une conférence au Collège de France ici, en lieu que j'ai pu appeler chez moi pendant 3 ans. And I'll also switch to English. It would be better for the talk, I think. So today I want to convince you that a certain perspective on strongly correlated electron systems, namely a so-called multi-method, multi-measure perspective, is very valuable and important to get the grasp on the physics. And I will explain this in actually 2 examples, namely where fluctuations are known and where fluctuations, so the dominating fluctuation channels, are unknown. And why is this interesting? Because strongly correlated electron systems provide fascinating examples of condensed matter systems. For example, high-temperature superconducting compounds, which also exhibit what is called a pseudo gap. We will hear from this in my talk and also in the talk of Michel later on. Quantum criticality and strange metallic behavior, but also the famous Mott metal-to-insulator transitions, and of course the topic of this series of lectures of Antoine, artificial materials, quote-unquote, so quantum simulators and cold atomic systems. What they have in common is they have fascinating phase diagrams, but it's a quantum many-body problem of competing fluctuations. For example, charge, spin, and pairing fluctuations. And if we want to know more and find out about these systems, actually, we prefer to apply a combination of analytical and numerical methods. And what I want to do in this talk is to bridge really this gap between, let's say, a situation where the fluctuation channel, the dominating, is actually known, which in our case will be the Hubbard model on a simple square lattice at half filling, to the situation where the fluctuation channel which produces in this interesting physics was a priori not known, and this will be the pseudo-gap regime of the Hubbard model actually at strong coupling. So in the first case, we will encounter that correlations can be tracked in multiple observables by multiple techniques, which led to this, this paper which Antoine was already mentioning before. And we will encounter an intriguing series of crossovers in this paper. In the second example, where the physical phenomenon is known but not its cause, I will introduce to you the so-called fluctuation diagnostic technique, which actually can be applied with also a multi-method perspective. So this technique is a certain set of post-processing technique, which then can determine unambiguously which physical channel is responsible for the physics. And the base of these works have been laid out in these papers. So let's start with the Hubbard model on a square lattice. So what is the Hubbard model actually? The Hubbard model is arguably the simplest model which can capture the essence of strong correlations in these systems. And it simply contains two terms in its Hamiltonian. So one is responsible that the electrons can hop from one lattice side to another, so that's a tunneling amplitude if you wish. And the second one is a very crude approximation of the Coulomb interaction, namely a purely local one, which is only active if there is a double occupation, so two electrons are sitting on the same lattice side of a crystal, one with spin up and one with spin down. And this model is quite easy to write down, but it's tremendously hard to solve. And exact solutions only exist in infinite dimensions. We will see the infinite dimensional solution in some minutes. But the last 20 years or so have seen tremendous progress in the numerical treatment of this so important model, which we recently summarized in this recent review. And on the numerical side, you have methods which basically fall into four broad categories. One are so-called numerically exact techniques. For example, lattice quantum Monte Carlo, where you simulate your system with a finite size and solve this exactly and try to extrapolate then this finite size to the thermodynamic limit. And tremendous progress has been also done in recent years by many of the people in the audience actually on the so-called Diagrammatic Monte Carlo method. We will hear from that by the talks afterwards much more, where you simulate or you make a perturbative expansion up to a very high order. And if you can resum this series, you also get the exact solution. Now, both of these techniques, out of various reasons, may be not applicable in every part of the phase diagram which is interesting to you. So, but they can serve then at least for benchmarks. So we also need approximate techniques. And of course, one approximate category could be mean field theories. I will explain this afterwards briefly. So static mean field theory, for example, random phase approximation or Hartree-Fock, or the celebrated dynamical mean field theory. However, these techniques can only accommodate or treat part of the fluctuations in our system. So in the case of the mean field theory, we have a static approach, but in the dynamical we can, so there's no fluctuations treated, but in dynamical mean field theory, at least the temporal fluctuations are treated. If you want to go beyond, one can extend these schemes in the means of cluster extensions and diagrammatic extensions. I will explain this in the course of the talk. And there is a fourth category of other common many-body techniques, like the two-particle self-consistent approach, functional randomization group, etc. So you see there's a whole zoo of these techniques available nowadays, as we know, as the members of the TRIX community here in the audience. So we thought it would be a great idea to take experts in each and every one of those methods and to apply their favorite methods on a test bed, which was picked actually decisively simple, namely the Hubbard model on a simple square lattice, and have computed some set of observables which we considered to be very important for this model. So the test parameters were the 2D unfrustrated square lattice in the half-field situation at a relatively small value for the Coulomb interaction, and we calculated observables like the coherence temperature, the pseudo-gap temperature, W cubancy, magnetic susceptibility, and correlation length there. So let me guide you first through the phase diagram, and then we take a look at what these methods give for these certain observables. So in this case, the phase diagram as a function of temperature and interaction looks like this. We only have one phase in a certain sense, a thermodynamic phase at t equals to 0, which indeed gives antiferromagnetic ordering. But the Merman-Wagner theorem prohibits actually ordering in finite temperatures. Nevertheless, we get a very intriguing series of crossovers when we come from high to low temperature. So let me guide you through this. At very high temperatures, we have the incoherent regime where we have not yet formed quasi-particles. And this we can detect via a self-energy, which looks atomic limit-like and is not momentum dependent. So I plotted here actually two momentum points, one at the antinodal point and the other one at the nodal point, so pi 0 and pi half. Both show this atomic limit-like behavior, and they show the same values as a function of the so-called Matsubara frequency. But if we now cool down progressively the system, we first gap in, so to say, the self-energy at the nodal point, as you can see here. And this simply means that I could be tempted to describe this with a Taylor expansion at low frequencies here. And then also in this regime 3, we gap in the antinodal direction. And this regime 3 indeed is then called the metallic regime of this phase diagram. If we cool down further, we can see that the antinode gaps out again, so it becomes divergent. And this is the phase or the regime which we called a weak coupling pseudogap. I will explain this afterwards, because it also suppresses spectral weight in certain momentum directions in our Brillouin zone. Finally, also the nodal direction gaps out, and if you gap out all the states on your Fermi surface, you have reached the insulating state. And let's see whether we can actually find these regimes also in our numerical calculations. And actually we did. So we did both diagrammatic Monte Carlo and determinantal quantum Monte Carlo, so this finite size simulation extrapolated to the thermodynamic limit. You can see two things here. First of all, you get all these 5 regimes, and these 2 methods which are exact, they agree as they should. So the exact methods capture our physics. What about now approximative methods? And there I promised you that we will start with a simple mean field. So this you know from your statistical physics lectures, of course. The static mean field or Weiss mean field theory, or Hartree-Fock. You can take, for example, the Ising model. You can take out one lattice site and average over the influence of all the other lattice sites, right? Like this, because you have no hopping here. There are no temporal correlations actually, but also no spatial correlations, because you create the mean field in space, so you average over all that, which technically means that your self-energy is just a number, which is then your Weiss mean field. And you now can extend this concept, and we have one of the inventors of this method sitting here in the first row in the audience, via the so-called dynamical mean field theory, where you take the Hubbard model, you take out one atom of this Hubbard model, and you create a mean field in space, but not in time. And like this, you keep all the temporal correlations of your problem, but you create a mean field in space, so you lose the spatial resolution in a certain sense for the self-energy. So technically, this is done by a mapping of the Hubbard model onto a single-site Anderson impurity model, which has to be solved, and fortunately enough, we have powerful methods provided by the TRIX library and by TRIX applications for doing that today, also numerically exact. So let's see what DMFT gives for this problem. Well, again, we have here the phase diagram as a function of temperature and interaction. You see that the static mean field gives actually an ordering temperature for an antiferromagnet, which should not be there in reality because we are in a two-dimensional system, but of course, mean field theory does not satisfy the Merman-Wagner theorem. But already in DMFT, the picture is very much enhanced. So you get these 3 different regimes in the phase diagram. One, again, this incoherent regime. The 3 is the metallic regime. And you get this antiferromagnetic dome, actually, which has a maximum at a certain U and falls often when going to higher U. So DMFT obviously also does not satisfy the Merman-Wagner theorem. But it captures already the crossover from the metallic to the insulating regime via a phase transition, so via a different mechanism. Also, DMFT knows about its own breakdown in a certain sense, because if you take a look at the magnetic correlation length as a function of the inverse temperature, you can see here, so of course in the numerically exact solution, you don't get a divergence of this behavior, but just a big growth. But in DMFT, you get a true divergence line which signals the nail temperature. So it indicates that there is something going on, and it indicates that spin fluctuations will be the most important channel to take a look at. DMFT is actually a very good approximation if you take it seriously, and in this case, I mean that you really enter the symmetry broken phase, because then you also can calculate the spectral weight within the antiferromagnetically ordered phase. And you see that actually the agreement between the numerically exact benchmark here and the DMFT is very good, although the mechanism of producing this drop in the spectral weight at low temperatures is a different one. In diagrammatic Monte Carlo, it's non-local fluctuations. In DMFT, it's the entering of the ordered magnetic phase. So DMFT is actually a very good starting point. What about fluctuations, so fluctuations in space? And there, a measure, of course, is the magnetic susceptibility and also the magnetic correlation length. So we can calculate this quantity, the momentum-dependent susceptibility, at the pi point, which is the antiferromagnetic susceptibility. and plotted here in this log plot over inverse temperature. And you can see in the numerically exact techniques, as I told you before, this quantity gets very large, but it's not diverging, so to say. So they respect the Merman-Wagner theorem. DMFT, as is the case for the magnetic correlation length, actually diverges here for this quantity, does not respect the Merman-Wagner theorem. What about now going beyond DMFT? So how can we include actually spatial correlations in our framework? And there are two routes to go. So one are so-called cluster extensions of DMFT. And here, the straightforward, which is technically not straightforward, but the idea is straightforward, to take out a whole interacting cluster of your many-body Hamiltonian and create a mean field in space again about this. This you can either do in real space, so you really take out this real space lattice, or in momentum space, and these are then called cellular dynamical mean field theory or dynamical cluster approximation, respectively. And like this, you keep the temporal correlations, which were already there in DMFT, but you also keep fluctuations in space exactly up to the cluster size, which we have taken here. So we have to solve basically a multi-site impurity model, a cluster impurity model, which we can again do via tricks. And the second route, actually, how you can extend DMFT for spatial correlations are so-called diagrammatic extensions. So here you can include also long-range correlations. How does this work? What you usually do is you solve your usual DMFT cycle with a single-site Anderson impurity model, but you don't only measure or extract from the single-site impurity model the self-energy or the local green functions, but you extract higher-order correlation functions, which we call the vertex, and then on this vertex we build non-perturbatively Feynman diagrams, for example, so-called ladder diagrams in the beta-salpeter treatment. And depending on which correlation function exactly you extract, there are several types of approximations and variants: dynamical vertex approximation, or D gamma A, dual fermions, dual bosons, triply irreducible local expansion, etc., etc. We will focus in this talk here now on CDMFT and the dynamical vertex approximation. So what do these methods give? And this now is a cutting-edge CDMFT calculation, and by cutting edge I mean an 8x8 cluster, which we can do at this half-field situation. You see that the agreement with the benchmark here, which is plotted in black, is actually improving, but also the CDMFT actually shows an ordering temperature. But this is logical because, as we will see in a minute, the correlation length in this situation will grow when you go to low temperatures. And then also the CDMFT only respects the Merman-Wagner theorem in the limit of infinite cluster size, which we do not have in this situation. The D gamma A here can actually treat also the long-range correlations. And you see there is a bit of a discrepancy, or a bit of an underestimation, let's say, of the magnetic spin susceptibility in this metallic part, but you indeed can go into the very low temperature part, and qualitatively this agrees with the qualitative behavior of the benchmark. So how extended are now the spin fluctuations? And this will be a very important question also coming to the second part of my talk. The extension can be measured via the magnetic correlation length, and this we can extract via a so-called Ornstein-Zernike fit, so in principle a Lorentzian fit around the peak of this magnetic susceptibility at the ordering vector. And if the peak goes narrower and narrower, our correlation length will be growing large. And as we can see here is, and this is, I think, one of the most important plots in this paper, because it shows a broad consensus among many of those quantum many-body methods. This correlation length is actually growing exponentially with what D gamma A predicts to have two exponential regimes, one in the metallic phase and the other one with a different exponent way into the insulating phase. So you have an exponential growth of the correlation length. And in the weak coupling regime, and I think this was also done in the lectures by Antoine, you can define a criterion actually for the opening of the pseudo gap in weak coupling, the so-called Wilk criterion, namely when the thermal de Broglie wavelengths of your quasi-particles or your wave packets is much lower than the magnetic correlation length, they will scatter quite strongly with these antiferromagnetic patches in your system, and they will localize, which creates the pseudo gap at the weak coupling, And of course there, if the correlation length is growing exponentially, you will always open a pseudo gap at low enough temperature. So you see these footprints of spin fluctuations in actually all observables on the 1 and on the 2 particle level. So coming to the second part of my talk, what is the difference to the situation when the fluctuations are not known? Can we find something out about our system when we don't know a priori the fluctuations like it was in the weak coupling regime of the Hubbard model? And actually, over the years, with a great team of researchers, we developed techniques for doing so, and one can pick out one particular example, namely the pseudo gap in, for example, the cuprates. And one of the hallmarks, of course, is this Fermi arc structure. So you have states depleted in some momentum directions, but not in the others. So the first one we call antinodal direction, the second one we call nodal direction. And this phenomenon has been attributed to actually spin fluctuations in some of the papers, to preformed Cooper pairs, but also to charge fluctuations. From this single particle picture, so from the spectral function, which can be, for example, measured in RPES, you cannot find out actually which of these fluctuations are opening the pseudo gap. But what we have to do actually is to raise the particle level description, so go from the 1 particle level to the 2 particle level. So what we can do is we shoot in 2 particles in our system, let them propagate and interact and take them out again. And if we do this in real space and imaginary time, we get what is the so-called 2 particle level green function. And we can separate this into connected and disconnected parts. We can extract the so-called vertex out of it. This is the main message of this slide. From this vertex, we could, for example, also calculate the physical susceptibility via the so-called bubble contribution plus these so-called vertex corrections. So if we have access to this vertex with our methods, we can do the following. We can connect the 1 and 2 particle level, not only in the weak coupling regime, but in every regime of the phase diagram by the so-called Dyson-Schwinger equation of motion, which is in exact relation connecting the full vertex to the single particle self-energy. So this is the formula, and this is, let's say, the Feynman diagram for this. So the basic message is, if we have access to the full vertex, we can calculate the self-energy out of the full vertex. So how can we tackle now this complex problem of analyzing the Dyson-Schwinger equation of motion with the F? Well, we can introduce changing of representations in the Dyson-Schwinger equation of motion. Namely, we could express this vertex, which is usually the up-down full vertex, in the spin channel, which is a combination of up-up and up-down, in the charge, and in the particle-particle channel, which is at a frequency transformation. Now, in this Dyson-Schwinger equation of motion, if we would do all the summations of these internal indices, we would actually get the same result for each of those representations. So these are equivalent to SU2 symmetry and crossing relations. But the big insight here was, if there is only partial sums which are performed, then we can get a physical insight about the problem at hand. How does this work? Well, we could, for example, omit the sum over the transfer momentum here in this formula. Then we would have a self-energy, which would depend actually on this external index, namely the transfer momentum. Or we could omit the sum over the bosonics or the transfer frequency. Then we would have a self-energy contribution, if you wish, which depends on the bosonic frequency index. And we can do this in different channels: charge, spin, and particle-particle. The first will give us so-called histogram plots in the next slide. The second one will give us pie charts. So if we apply this now to the Hubbard model, and in this case it was to the Hubbard model with 6% doping, it is, let's say, realistic parameters for cuprates in the strong coupling regime. So U is equals to 7 now, and the technique was a dynamical cluster approximation with 8 sides. What you see here is that you again get for the antinodal direction a divergent self-energy, and for the nodal direction a Fermi-liquid-like self-energy. So you indeed have in this definition a pseudo gap here. What can we learn now from these partial summations? Well, we see here we can do the representations in the spin, charge, and particle channels. And what you see here is that at pi for the antinode, we have the largest contribution in the spin channel and in the particle, in the charge and particle representations. This distribution is equally spaced. So if you would sum up, so to say, it would be a rather short short or not that intense peak giving in your self-energy. The same is also true for the antinode, for the node. So in this case, one can say that the spin wins, and if we take a look now at this pie chart, so in the frequency representation, we also see that the zeros Matsubara frequency is actually giving the strongest contribution in the spin picture, and in the particle-particle, as well the charge picture, which is not shown, this is distributed among the first 5 or 6 Matsubara frequencies. So to summarize, we get actually a long-lived fluctuation in the spin picture, whereas we get this day-fly or short-range, short-lived fluctuation in the other pictures. So in this case, we can say that the spin fluctuations are responsible for opening the pseudo-gap. And to bring the context again to multi-messenger studies, this has been also shown in different other contexts and techniques. So this is again a calculation with DCA with 8 sides. And you see here, this is a whole scan of the phase diagram. In the charge picture, you have an equal distribution amongst many of those momenta, whereas in the spin picture, you have a clear peak, so to say, for the antinode and for the node. So again, the spin picture is the representation which describes the situation the best. And to make the connects to the next talk of Michel, actually, there has also been this beautiful work of Weiwu, Antoine, and Michel on diagrammatic Monte Carlo, so a numerically exact technique, which also used then this fluctuation diagnostic approach. But they, of course, have the full momentum resolution here. So they could calculate these contributions among the whole Brillouin zone, and you see there is a big contribution at the antiferromagnetic ordering vector in a regime where diagrammatic Monte Carlo could show that there is indeed, again, a pseudo gap. And there's been a lot of other works, actually with many different techniques, who are using this framework of the fluctuation diagnostics method, again, pointing out the importance of multi-method studies in this context. So to summarize, what I wanted to achieve is that I can bridge the perspective of multi-method studies in the context of models where, or materials where fluctuation channels are known to the unknown territories, if you wish. And the outlook would be that there were already recent extensions of this fluctuation diagnostics, for example, for ordered phases, but also for real space correlations. And this provides, in my opinion, a big opportunity for exploring unknown territory, for example, in cold atomic systems. So with this, I want to thank all my many collaborators in these 2 projects, and of course, you for your attention. Thank you very much.